So I think we can start. And I introduce Professor Remo Ruffini. Unfortunately, I'm not able to report all his scientific activity because this would take a time longer than the seminar itself. But in any case, he's an interesting person. He did some very important things. Sometimes our roads have crossed. We have cooperated. We have fought also in the past. But he has just remembered something that he did that made feasible the Bepo satellite. Probably he has forgotten that the first grant on to do a participation to an X-ray polar emitter was given by a committee whose he was the chair. I don't know, probably you have forgotten, but no, I haven't, because this was the first money I got for research.
I did not forget, and the most important point is that you did not forget.
Anyway, in this institute, we work on some topics, I don't know. I know that through polarimetry and especially through timing, we hope to make some fixed point about the neutron star equation of state. And of course, everybody knows that in the past, one very, very important theory was developed almost half a century ago by Remo and by Rhodes. And so he worked with the gamma burst, he worked on Crab, and for sure, many of the things that we are working on in this institute have been seen a contribution, an important contribution by him. Apparently, now we should expect something very important from this seminar. So please, Remo, go on.
Well known, the Crab. Well known, the pulsar. Today, we can look back to this object with a completely new eye. Same object, but new science after the gamma ray understanding, the gamma ray burst understanding. The story dates back many years. Let me, there are very precious moments. I don't have time to look too much in the history, but still I like. The Crab was discovered in '67, just after I arrived in Princeton, working with John Wheeler. He dedicated to me, John Wheeler is first on the right, daughter to you. Introduced me to his group. And the Crab was the object of research in Princeton by Wilkinson. W map, you know, in cosmology, was Wilkinson map, one of the greatest results in cosmology. But at that time, he was working on the second derivative of the pulsar in the Crab. And I was fascinated, and at the time, because I noticed that if you take a neutron star rotating at 33 milliseconds, then necessarily in the early part of the pulsar, in 1054, it should have rotated at a millisecond. And to rotate the star at a millisecond, it takes some implication. because the system cannot keep symmetry, but it can create a triaxial ellipsoid. And this was my paper with Ferrari, that the crab necessarily, when it was born in 1054, it must be a triaxial ellipsoid. I wrote a paper and with Ferrari, with Attilio, and we submitted to APJ. Wheeler was initially not sure that it should be published or submitted from Princeton in APJ, such an idea. And he asked Wilkinson, he said, should we send? And Wilkinson said, of course, it's extremely important. Now, the proof that was very important is that, I don't know how many of young people know, there was an exceptional editor of APJ. His name was Subramanian Chandrasekhar. And all the work of, not all, but the majority of the work of Chandrasekhar was dedicated in continuing the work initiated by Maclaurin, Jacobi, Riemann. Everybody who was a great mathematician was challenged by the rotating figure of equilibrium. And there is a fantastic idea by James Jeans. I invite all the young people here, or not the young, but even the old, to read the book Problem of Cosmology and Stellar Dynamics, because it's extremely important, beautifully written. And there you said, Jean said, we may with fair confidence assert that the two-dimensional series end by fission into two detached mass, and in view of the closer parallelism which you discover between the two-dimensional and three-dimensional problem, it seems highly probable that the three-dimensional series also will have a similar fission into detached mass. This is written by James. Well, one of the key points that we are observing from gamma ray burst is that very likely this is correct, but it's a completely new outlook to the supernova and to the pulsar. And at the end, maybe I come back to this. The first evidence for this triaxial ellipsoid, clear evidence, is in GRB 220101. I will try to show you that, but it's the end of a long, long story. Let's try to go on more quickly. The other fundamental contribution which we did in Princeton, of course, this everybody knows because we introduced that in the black hole idea with John Wheeler all over the world. But what people, and of course, one of the fantastic things about the black hole theory was the work created by this student. You're too young to know Eugene Wigner at the center. I am in the center there, the back, Wheeler, and so forth. Even people who later on took the Nobel Prize. And Dimitrios at that time was 19. He came to Greece from Greece at 16, 17 he finished undergraduate, 18 finished the graduate school, 19 published the paper with me. And this paper was written was based on the Kerr metric. Well, based on Kerr metric, mathematica, historica and this one. This paper of Dimitrios and myself led to the mass formula of the black hole. This one. Neck to neck. The first paper, 70, then Ruffini, then Hawking, and then Hawking again. But the difference between these two publications, obtaining both this mass formula, is only 10 days. The formula indicated, now I care about this because this is a long story, but only yesterday we have written, thanks to the collaboration with Dr. Ueda and with a very young student from China, Shubui, we have understood something fundamental on this formula. What is the importance? You see, L is the angular momentum, E is the charge, M is the mass, S is the surface area. The surface area of the black hole increases due to the Hawking theorem. But due to the Hawking theorem, also the reducible mass should increase. And up to now, people have used our mass formula to extract the rotational energy. There are thousands of papers, of books, and so forth, how to extract the rotational energy from the black hole. But they missed to consider the fourth quantity, the reducible mass. I don't go give this lecture, I will not take into this, but we finally understand the role of the reducible mass. And this shows that many of the processes in the literature cannot be used because the increase of the reducible mass is too big and it spoils the rotational energy. However, in the model we have made for the black hole in the jet radiation in gamma ray burst, everything is safe because the change of the reducible mass is very tiny. You agree? We have written this. Okay. So I think even that gives you a flavor how the ellipsoid, how the reducible mass related to the rotational energy extraction can be important. A new era started with the Italian Dutch. Actually, maybe we should have the courage in the future to just call the Italian satellite Beposax, because we all this make clear Dutch in quotation mark, okay? Because they use the satellite, but not to build the satellite. We just associate in a single map and so forth, improve the GRB location with using X-ray afterglow, the new fundamental component introduced. The film determination of the GRB cosmological origin, everything was following from the work of Federico Costa. This was a turning point of astrophysics. But also very, very important. Okay, all this is known, and I am, of course, I usually show this picture. I mean, thanks to Enrico, we understood that these objects were cosmological and the energy was 10 to the 54. This is no joke. It's a turning point. And in addition, there was another turning point, which to me, since the beginning, fascinated me. The fact that some GRB, for example, this beautiful one of 1998 supernova, is associated with supernova. And this, here you have the X-ray emission, here you have the supernova. This is not real. Of course, all the model up until then, Mezzaro, Rees, company, used to say that the GRB originated from black holes. Of course, I was happy that black holes were considered because I introduced them, but I was very unhappy because the fundamental point that some GRB and some supernova coincide. It cannot be, and you cannot obtain a supernova out. Okay, you will read now the history, the rest of the history in the article which is coming out tonight in Astroph. And our focus. The exponential growth in the MJF prolific exponential growth of that analysis led to the binary-driven hypernova model, which was started by the concept of induced gravitational collapse by Rueda and myself, and evolved. I cannot say how more important and fundamental were the contribution at the time of Los Alamos Laboratory and Chris Pryor. Why? For us theory, the data were not many, but Chris had the fundament of the supernova, and the model we start to develop is binary-driven hypernova, was based on a CO core of roughly 10 solar masses with a companion neutron star in a binary, 2 solar masses. And it assumed our model that the CO core of 10 solar mass collapse and generate itself a new neutron star. Therefore, you have a CO core, a neutron star around, which we discussed at lunch. Hope you followed and agreed, is the progenitor. But in addition of that progenitor, the CO core collapses. And by fission, creates a new neutron star. This is the new fundamental theory. The new neutron star with a mass 1.5, which spins initially at a millisecond period. This new neutron star gives origin to the afterglow emission observed in the X-ray, optical, and radio in all BdHN time. And this implies that the process of emission is practically spherically symmetric. And their analysis has been made proof. What we have done, okay, this is the model. We did not have data before. We obtained the data from gamma ray burst, and now we are gaining independence. But in the beginning, we were mainly based on numerical simulation after the largest possible computer in the world, who had the model of a 10 solar mass explosion of supernova by Chris Pryor, what they had developed, and in their code, we inserted a binary neutron star companion. And seeing how this the collapse of the supernova leads by fission. We did not add the theory, now we have at the center of the binary driven hypernova, c'è un pulsante da qualche parte, un indicatore, se non un bastone, the point is, here you have the supernova expanding, the shell. Here is the new neutron star nearby accreting and lately developing a black hole. And at the center, you have the new neutron star. Here there are different visions of this system. But this has been fantastically important because we could model understanding the physics and at the same time feeding back and forth to test in Los Alamos this result. This has been tremendously important. But in the meantime, we were doing the understanding this is another system, again binary, in which you have the supernova exploding, here the new neutron star, here the companion neutron star, accreting, and then bit by bit creating a black hole. Therefore, already at this stage, Enrico, the model had the two big components. One component, the accretion on the neutron star creating a black hole and emitting eventually JEV radiation with electrodynamical process, and the new neutron star at the center at a millisecond period creating the afterglow. These are the two components, the X-ray optical afterglow by the new neutron star at the center, and the rest just by the black hole, if it exists, or a companion neutron star. Okay, let me go to this result. One of the most important new results which we obtained last year was to study the supernova associated, the supernova associated to long GRB. And we study a family of this supernova. Here we have the table. I don't want you to memorize, but you will find them. You will find them in this AstroPH of tonight. What is the incredible result? Is that you look at all different supernova. We took only 29 of them. As a function of redshift. And the luminosity of this supernova is practically 1 per second, independent of Z. And is always the same. And this is the peak luminosity of the bolometric light curve of the supernova. Very little spread. Another very beautiful quantity is the time of occurrence of the peak of the supernova from the trigger of the GRB. Mi segui? And the standard, always the same for all the supernova, 10 to the 6th second. Therefore, if you look at the energy, the luminosity, and the time of occurrence, the energy of this object is 10 to the 49 of this supernova. Standard, independently of Z. Now, the next, we take the same previous plot of the luminosity per second, 10 to the 6, 10 to the 49, and we compare with the e-ISO of the gamma ray burst. And while the energy of the supernova is unique, 10 to the 49, the gamma ray burst, this has been for many years a mystery, are completely different energy, and they divide in 3 classes. And the major effort has been to understand these 3 classes of binary-driven hypernova, with the first class from 10 to the 47 to 10 to the 50, second class from 10 to the 52, 10 to the 52 to 10 to the 54. What is the underlying physics which explain this difference? And this is where our work on gamma ray burst started. The BdHN I have range between 10 to the 52 and 10 to the 54 hours. The orbital period is logged at 5 minutes. And the binary separation between the CO core and the neutron star is of the order of 10 to the 10 centimeter. The hypercritical accretion of the supernova jet onto the companion neutron star leads to the critical mass, forming a Kerr black hole. The energetic of 10 to the the BdHN I, larger than 10 to the 52, originate in the rotational energy of the uniform black hole and in the X-ray energy of the afterglow. Okay. You will see a few examples of GRB. 180720b, the first example, in which what we have done is an in-depth analysis of the luminosity in the different band, in radio, in the optical, in the X-ray, and in the JEV. And what is the important point of our analysis is that we have understood the new physics related to 9. We have done the spectral analysis of the different parts. You see here all this line. We have divided the typical gamma ray burst in 7 episodes. And these 7 episodes are the spectra, which are completely different, one by one, and different energetic, and especially different physical property. Mi segui? Ci sei? These are some of the spectral analysis of the new neutron star rise, of the UP and UP1, cavity, and all the different episodes which have a different spectral structure. And for these sources, we have 7 different episodes, and each one characterized by this energy and this spectra. And the physics of these objects are completely different, the spectral characteristic as well as their physical nature. Remo is here. He has been with Fateme, has been essential in understanding the structure of the ultra-prompt emission, this emission in the MEV in the first second of the GRB. And the afterglow, of course, has been the study of the afterglow for the mission of synchrotron has been done specially by Orgerweda and collaborators. And also the entire spectral analysis has been done by Yang Li with Wang Liu, using their expertise in the spectral analysis. This is the author system GRB 1901-14C. Again, where you have the birth of the neutron star here, UPA1, UPA2, the cavity, and the corresponding energetic for all this. And also new phenomenon, namely when we have looked at the UP phase of 1901-14C, we have found a total new physics, conceptual physics, of some similarity, a fractal structure in the spectra. Well, you will see all this expressed in the article. But in addition, of course, for each source we have understanding the energetic, the time, the spectra for all this, and the underlying physical process, the synchrotron process for the afterglow, the birth of the black hole, the emission of the black hole, the emission of the J radiation. Just to show you that we have reached a complete understanding of this very first family of BdHN I, where the accretion of the supernova onto the companion neutron star generates the black hole, and the fission of the collapse creating the new neutron star generated the X-ray afterglow. But they are systems in which the binary system is longer than 5 minutes or 10 minutes. And in that case, the black hole is not formed. This is a BdHN II. The energetic is much lower. The binary period, instead of being 5 minutes, is 20 minutes. And the characteristic energy is not 10 to the 54, but 10 to the 50. Also, in this case, the afterglow is always present with the characteristic synchrotron emission in X-ray, optical, and radio. And instead of starting at 1 millisecond, you start around 5 or 6 milliseconds. Then there is a third family. This is an example which we have published in APJ of this source. And then of this table also characteristic of the 7 episodes. In this case, there is and then the BdHN III, system still weaker in energy, with binary period still longer, and the millisecond pulsar between 50 and 100 milliseconds, which can be sufficient to explain the X-ray afterglow. And in all this system, of course, we always see the supernova bump of the supernova at 10 to the 6 second. Therefore, this is the scenario of all different gamma ray bursts. From then, I don't have, well, you will find all this in the publication with the corresponding table and the corresponding publication. We have some other publication, more, 500, 600 publication. But in these last days, we have a tremendous interest. Okay, this is published. It's submitted for publication AstroPH. There are many papers supporting, but now we have two new sources, GRB 220101 and 221009A. These are fascinating. 22, we publish 2 GCM for the first, 4 GCM for the second one, and we are getting along in preparing the papers. Why we are so excited about this one? This is a petonova, we call it. It's not a kilonova. It's hypernova. It's a petonova. It's an energy still big, around 10 to the 55 Earth. And here you see the corresponding afterglow for these 3 different GRB, 190140C, 180720B, and the red is the new one. But there is something even more exciting about this system. I don't know if I have inserted. Yes. This is the work of the last hours. I can just tell you why we are so excited. We cannot tell you details, but we can. Raim has done this yesterday. It's not so. And I think the most exciting thing for us is to go back to the old paper, my first paper. This is the first example in which we see something that Chandra was very, very excited. That if you have a rotating off object like a Jacobi sequence, the Jacobi sequence loses rotational energy but speeds up. Well, we will show that in the publication, but here we have the first example of the speed up of the triaxial ellipsoid. You agree? It's the only thing to tell at the moment. The other source, of course, is 220109. We expect the data from Lazo, from Kautze at any time. He told us yesterday that he got 3 referees from science, all enthusiastic, but our prediction is that this time radiation should be in that band. Before going further in the model, we are expecting the publication of the data, but also in this case, there is a lot of new science. I cannot go more detailed than this. Here you have as usual, the emission in the X-ray, the emission in the optical and the radio, 1 point in the radio. Do I recall correctly?
Purple is red. Purple is red.
This one.
That blue is the expected supernova.
This one. Excuse me. Oh, that is the expected supernova. Yes. And where is the radio?
Purple.
This one?
Yes.
This is the expected supernova, and this supernova cannot be seen because the afterglow in the optical is way over. Anyway, this is ongoing work that we are doing using the knowledge that we have acquired from the previous there is a change of paradigm, a fundamental change of paradigm based on all the understanding that we have gained in gamma ray burst. The discovery of GRB 220109, 221009 has offered the possibility to obtain data close to the GRB trigger in the long GRBs, and consequently progress in the theory of the supernova explosion and of the millisecond period and the formation of a new neutron star by fission from the CO core and pulsating at millisecond period. This leads to the observed pulsar and to the multi-wavelength synchrotron emission in afterglow. This procedure, unlike the traditional approach of the supernova explosion, which were based on the nuclear physics process in non-rotating spherically symmetric systems, focus on the fundamental role of rotation induced on the CO core by the binary neutron star companion. This CO core collapse leads naturally to the transition from a Jacobian ellipsoid triaxial to a Maclaurin spheroid near the occupation point, probing the ultra-relativistic quantum electrodynamical process in the collapsed emission, also gravitational waves. This is also very interesting because it's the first system which in principle should lead to a marked signal of gravitational waves with a characteristic frequency and intensity, and exactly identify the moment of origin. The supernova accretion on the neutron star binary companion leads to the formation of a black hole originated on average from radiation of the long GRB, utilizing the rotational energy extraction of new Volcker black hole. The plan is not to rely any longer on simulation based on theoretical model only, but infer the nature of the supernova explosion, a model-independent picture using the data of GRB as close as possible to the GRB trigger. This is a change of paradigm. And we will see that in the time to come. We have enough data to tell for the first time, not to make a model about this, all the opposite. Take the data, see when the new neutron star is born, take the data, see when the black hole is born, tell the data what the characteristic of that explosion is. And the origin of that energy is the rotational energy with the electrodynamic of the associated magnetodynamical effect, of course, but is completely alternative to all the understanding that is commonly, but it's a new era because we have enough data now to approach this new science and new physics. Of course, all what we have said is valid also for the physics of anti-galactic nuclei, and everything since the early day in Princeton, Kerr solution, black hole formula, all the recent work on energy extraction from GRB, but the black hole formula especially is based on our standard idea and Kerr solution. It's fantastic that after 50 years we find necessity, detailed necessity to use Einstein theory precisely and Kerr solution. It's incredible. And now the harvest comes for the new epoch also of understanding that concept which when Christodoulou obtained the mass formula I introduced the irreducible mass. And finally, we are writing a paper explaining the limitation of the irreducible mass. In Pescara, we will discuss this, and in Armenia as well, also this aspect. And Shurui will finish to write the paper. I don't know which one is the most fundamental contribution. Probably the most intriguing one is the one of the irreducible mass. All the rest has been beautifully, but quite natural. But this one is really very, very intriguing, very fundamental. Time for enjoying further. That's it.